So this afternoon, we're going to talk about two concepts. One of these would be significant figures, and the other one is scientific notation. Probably we're going to talk first of significant figures since scientific notation is going to use the concept of significant figures. Okay? So there are rules. I don't know how many rules are there in your modules class. In order for you to determine the number of significant figures, and so how many rules are there? 4, 3. Three, three. Okay, so let's start with um, the first rule. Never mind with this one. Okay, the first rule is significant. Not this one. Okay, James is with us already. So the first rule there, according to what the rule says, all non-zero digits are always significant, isn't it? All non-zero digits are always significant. And what are the non-zero digits? What are the non-zero digits then? The numbers 1 to 9, no? 1, 2, 3, 4, 5, 6, 7, 8, 9. They're all significant digits. That's rule number 1. What about rule number 2? Can you tell me what's rule number 2 there? Um, Alan, what's rule number 2 there?
Uh, Zeros between other significants. Wait. I'll do it again. Zeros between two other significant digits are significant.
Okay, so thank you. So if you look at the illustration here, class, we have zeros in between the significant figures. No? As mentioned by rule number 1, all non-zero digits are significant. How about number 2? Zeros in between significant digits are significant. Therefore, the zeros here are significant digits. Just since they are in between significant figures. Okay? So in this example class, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 significant figures. Again, all non-zero digits are significant. Rule number 2, zeros in between significant digits are significant. Let's proceed to rule number 3. I'm distracted by the multiple voices I hear. Okay. Rule number 3 in your module, can you read that for me, Edson? Rule number 3.
Rule number 3. Zeros that precede the first non-zero digit and tell the location where decimal point are not significant.
Zeros that precedes the decimal point that determines the decimal itself are not significant. However, can you consider reading the next rule there, Edson? Please continue the reading.
Zeros at the end of the number may or may not be significant.
Okay.
Zeros at the end of a
Continue.
zeros at the end of a number are significant if they are to the right of the decimal point.
So thank you, Edson, for reading steps. Good afternoon, sir. I didn't receive any module anything. Okay, so after this session, or probably I'll send it to you through online chat. After this session, I'll send you an online copy of the module so that you'll be reminded, okay? Okay, so zeros that precedes a decimal point, in this example, this is a zero that precedes that said decimal point, and this zero simply determines the position of the decimal point. Thus, this is insignificant, not significant. However, zeros to the right of a significant digit are significant. In other words, the red marked zero here is significant, while these zeros here are insignificant. Okay? And they are significant, it is because the zeros to the right of a significant digit following the decimal point makes it a significant digit. So even if you're going to say for sure class 0.003, how many significant digits are there in this number? It only contains 1 as a significant digit. If you have the number 0.0030, how many significant digits are there in this number? 2 already, these 2. Okay? So therefore, in this example, how many significant digits are there? This example class. 1, 2, 3. So this is 3 significant digits. This one, it contains 5 significant digits, making it 1, 2, 3, 4, 5. Okay? According to the rule class, zeros at the end of a significant digit may or may not be significant. Okay? So let us continue this slide class. So for us to understand that, is it the last rule, Edson? No, it is not. So this one class, zeros in between the significant digit are significant. They're always significant class. Diba? So if you look at the examples here class, the 1 here is significant, the 0 here is significant. Therefore, this 0 in between is also significant. What makes this 0 significant? What's the difference between that number and this number? If I will write this number class, 0.01. What's the difference? The number of significant figures here is just 1, whereas the number of significant digits here is 3. Why is that so? Because this will follow rule number 2. Was it rule number 2? Zeros in between significant digits are significant. So this is a 0 that is between a significant digit. Also, this is significant because this is a 0 to the right of a significant digit that precedes a decimal point. But this 0 is insignificant because this will only determine the position of the decimal point. Unless, if we write here a number, then the number of significant figures here will become 4, making the two zeros in between, the two numbers 3 and 1 are significant. Similarly, these two are significant and these are also significant. Where is that condition wherein Edson says may or may not be significant? How can we illustrate that as an example? Okay, this one. Zeros used only for spacing the decimal point are not significant. This is the time when you consider the condition may or may not be significant. At this point, we have 100, and you know how many significant digits are there in 100? It is only 1. In other words, this is not significant. In the same way as this one, these are not significant, so the only significant digit here ends up with 3. Okay? Also, class, put this in mind. The way you write a decimal properly. Okay? Example, this one. We have here examples. 0.247 is written properly. 0.0042 is written properly, but 0.873 is not written properly as a decimal number. What makes it not proper? With this illustration class, you should have a 0 that precedes a decimal point. Even if this is insignificant, but this is supposed to be written to properly write a decimal point. Get it? So that is why for answers which are expressed in decimal, you always have the notation decimal point in between 2 digits, either significant or not significant. If the decimal number is less than 1, then you have to place a 0 before the decimal point. Question? Clarification, class. So let's have this example. How many significant figures are there in number 1? Let, can you unmute yourselves if I will be asked? Alona, how many significant figures are there in number 1?
3, sir.
3? The answer is
3.
just 1. You only have one significant figure in number 1. And that is only 4. Okay. How about number 2? Allen. How many significant figures are there in number 2?
Or sir?
The answer is 4, correct. So see the difference between number 1 and number 2 class.
Yeah.
Basically, they're just the same. Diba? However, the presence of a decimal point makes it different from number 1. Okay? So, in number 2, you have 4 significant digits, but in number 1, you only have 1 significant digits.
So Jet,
Yes, Vicky?
the example in number 4 in the module is 2.00 centimeters or 2000 centimeters.
I will share screen the module. I don't have the copy of the module in my hand. So, Rowan, let me share screen. Example number 2, Miguel.
About significant figures.
Okay.
Number 4,
Number 4.
2000 centimeters or 2.00.
Where?
There, sir. Kanang number 4 is a significant figures. Kanang examples.
Akin eh? 2000 cm.
How come only one significant figure and then 200k? 4 ba to or 3?
4, yeah. If you look at this example class, kindly look at your module. If you compare examples 2000 cm and 3000.0 liters, the number of significant digits here is just equal to 1. But in 3000 liters, the number of significant figures is 5 because of the presence of the decimal points. That's the only difference there. Okay? Let us review the rules then for us to understand. Rule number 1, all non-zero digits are significant. Whether they're located to the left of the decimal point or to the right of the decimal point, then they're all significant. Rule number 2, zeros between two other significant digits are significant. So these zeros that is located in between two significant digits are significant then. But zeros that precede the first non-zero digit and until the location of the decimal point are not significant. This one is not significant. These zeros that precedes the decimal point simply tells us the location of the decimal point, and this is not significant. This is also not significant. Okay? But zeros at the end of a number may or may not be significant. In what way they are significant? If it precedes or it succeeds at a significant digit. For example, this is a significant digit, right? And these zeros follows a significant digit, making the 9 here significant. Get it? But this is not the succeeding of the numbers 53. Instead, this precedes the digits 5 and 3, so this 0 is insignificant. Get it? Also, class, let's look at the decimal point. Zeros, this one, zeros. Okay. Zeros at the end of a number are significant if they are to the right of the decimal point. Again, zeros at the end of a number is significant if they are to the right of the decimal point. The end of a number which is a significant number. Get it? So let's look at this way. This one is a significant number. But following that number is a 0, which makes this insignificant, which has the number of significant digits, which is only 1. But in example number 4, the third one, this is a significant digit. This is a 0 after the decimal point, see, to the right of the decimal point, which follows that this is after a significant digit, making this number significant. Thus, the 3 zeros in between will become significant following rule number 2. Understand? So it's basically the presence of the decimal point that matters. But, sir, is it the same 3,000.0 liters and 3,000 liters? Yes, they are just the same. But with respect to the number of but the number of significant digits, they don't have the same number. 3,000 has only one significant figures, while 3,000.0 has 5 significant figures. That's just the difference there. Okay, so you unmute yourselves if you have a question, huh? Let's proceed to number 3. Number 3, Lucia, how many significant digits are there in number 3?
Sorry.
1.
1, correct. So number 3, it only contains 1 significant digit. Number 4, Edson, this is very hard.
Yes, sir.
3, this is 3. Number 5, Vince, how many significant digits are there in number 5?
3.
The answer is 2. 2 only.
2.
So this one contains only 1 significant digit. This one contains 4 significant digits. Number 3 contains only 1 significant digit. Number 4 contains 3 significant digits. But number 5 contains 2 significant digits. Only the 3 and the 2. Okay? Number 6. May I ask Sean, how many significant digits are there in number 6?
Liter.
3, correct.
No,
It contains 3 significant
I
digits.
see.
I heard you answered 3. Sorry, Sean. How about number 7? James, number 7, how many significant digits are there?
5, sir.
5. And Miggy, how about number 6? Number 8, Miggy. How many significant digits are there?
6.
Very good. This is already 6 because that 0 is already to the right of a significant digit, which is to the right of the decimal point. Okay? Oh, sorry. 6, 6, 6 pala. Questions? Clarifications? Please unmute yourselves if you have a question, if you have a clarification. And this is actually the basis of how we are going to identify the way in which we're going to write a scientific notation. And speaking of scientific notation, the next examples includes a scientific notation. Let's see a chat. This one. This one, class. How many significant figures are there present in the following numbers? Let's start with number 8. Number 8, you only have 2, obviously. Number 7, you have 4 significant digits. How about number 6? Christopher, how many significant digits are there in number 6?
2, sir.
2,
2, sir.
The answer is 2, correct. Very good. The answer is 2. How about Alona? How many significant digits are there? Oh, I'm done with Alona pala. We have Jaika, Jana, Maika. How many significant digits are there in number 5?
3.
The answer is 6, Jana. Okay, they have. It has to have 6 significant digits. Why 6? Why 6, class? It is because the problem or the given starts with a significant digit, which is 65. And since the zeros here is to the right of the decimal point that follows a significant digit, so this zero is significant, and between the zeros or the zeros in between are also significant. Therefore, this is 6. Number 4, let's try
Seven.
Edson. Edson, how many significant digits are there in number 4?
Answer. 1.
Very good. It's just 1. It's just 1. How about number 3? Alona, number 3.
12, sir.
1 as well. Even if you're going to make it in numbers that is 5 billion, di ba? 5 billion. Ano na siya? 1, 2, 3, 1, 2, 3, 1, 2, 3. Thousands, millions, billion, trillion, 5 trillion. Even if you're going to expand this into 5 trillion, these numbers are still insignificant. And the only significant digit is 5, which is 1. Okay? Ay, kalimuglon. Next one. How about number 2? Nick Luciliano. We have Nick here. Do we have Nick? Number 2, Nick. What is the answer here? How many significant digits are there? Please chat your answer, Nick, if you can hear me loud and clear. You can chat your answer, huh? If you cannot unmute yourselves. It's James, James. How many significant digits are there in number 2?
In number 2, sir, there are 3.
3, correct. So even if you're going to expand class, look at the exponent, negative 8. So that is 0 0.1, 2, 3, 4, 5, 6, 7, 8. That is the number. These zeros here are still insignificant. No? And the only significant digits are 1, 6, and 7. The same goes with number 4 and so on. And in number 1, it's just 1 significant digit, which is 4. Get it? So what do you think is the clue how we are going to convert a number to its scientific notation? By the way, class, this is a scientific notation. So let me just put this as an overview before I go to discuss scientific notation. Scientific notation is simply writing the number of significant digits and then count the number of places from the decimal point to where we're going to place the decimal point in our scientific notation. No? Either positive or negative, it depends, the direction depends from it. Clarification regarding this discussion. So you can clearly determine the number of significant digits from questions regarding the scientific notation, significant figures class. So if there's none, then let's proceed with how we're going to write scientific notation. What's that?
You can make it appear ridiculous and funny.
Mga kulinig.
Our side should blend it later because we all look so fresh.
Okay, so let me share screen.
After our machine.
Mga
There are two unprepared machines. But look at us. How else can verify a prepared later than this?
Okay,
You can make it appear.
this one class. Can you see the slideshow?
I will do it.
Can you see the presentation class? Chris, can you see it properly? Okay, so this time around, we're going to discuss what is a scientific notation. So scientific notation makes a bigger number looks smaller by how we're going to write it. For example, class, we have here an ordinary penny contains about 20, I'll read this one, thousands, thousand, million, billion, trillion, 20 sextillion atoms. Imagine that. So the amount of atoms present in a one penny is 20 sextillion. And the average size of an atom is about 0.00000003 centimeters across. So these numbers could probably confuse us if we most of the time write these ones. Especially if you're going to add values class, like you add 25 sextillion, 400 quintillion, and so on and so forth, to 24 septillion and the likes. That problem could end up with a very lengthy solution, especially that we involve bigger numbers. That is why we're going to introduce the concept of scientific notation. Scientific notation is a shorthand way of writing such a number. So how are we going to write the number of atoms present in a penny? How many significant digits are there in 20 septillion class? You only have one. No? According to the rule, remember the rule class. The rule in writing a scientific notation is that move the decimal point after the first significant digit. Again, move the decimal point after the first significant digit. Can you repeat what I just mentioned? James, what was the rule there?
The number when ano sir is that there is only one digit when you are shortening the ano sir.
See, you're not listening to me. This is the problem when you are with me. You are physically present, but probably what you're doing there is using your cell phone, playing ML or whatever. No, listen properly, James. What
Sorry
was
sir.
the rule there again, Edson? If you don't mind.
In the ano sir,
In
the one with the
changing a number to a scientific notation.
you count the number of zeros.
See, so no po naminaw. I don't know with you guys, but I mentioned the rule in changing a number to a scientific notation. Move the decimal point after the first significant digit. Okay? Again, move the decimal point after the first significant digit. Between the numbers 20 sextillion. How many significant digits are there in the number 20 sextillion class? You only have one, which is 2, right? And where's the decimal point in the number 20 sextillion? It is located here. Yeah? And even if we're going to write a 0 here, 2 is still our first significant digit. Again, the rule there is move the decimal point after the first significant digit. In the number 0.00000003, how many significant digits are there? You only have one as well. And that is 3. So therefore, this decimal point will move after 3. As it is said in the rule, move the decimal point after the first non-zero integer, after the first significant digit. Okay? So asa my first significant kan what's the first significant here? This one. Okay? And that will end up with this number. That the scientific notation of the number of atoms in a penny is 2.0 times 10 to the power 22, and the size of an atom is 3.0 times 10 to the power negative 8. Okay? What have you observed with the scientific notation class? What have you observed there? The exponents, 22 and negative 8, right? Notice that it is positive 22 and then the other one is negative 8. Huh? So let me give you a little clue there or a hint there. The sign of the exponent will tell you the direction of the decimal. For a positive exponent, it means that the decimal moves to the right. Positive to the right, di ba? In a Cartesian plane, positive x goes to the right. Di ba? So therefore, the positivity of the exponent of the scientific notation tells you that the direction of your decimal point moves to the right. And then the negative exponent means the decimal point moves to the left. How is that motion, class? That is from the scientific notation to the decimal notation. Um, let's let's do it in this way. Example, we have 2.0. Wait. Where's the annotation? Here. So 2.0 times 10 to the power of 22. To check if your answer is right, let's try to move the decimal point to the right. Okay? And since the number is positive, so let's move the decimal point from here to the right. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. And then write the number of zeros there. Zeros, 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 and so on and so forth. So that is how you're going to convert this scientific notation to decimal notation. This is a decimal notation, the previous example. And then for the negative value, if this is your original scientific notation, if the exponent is negative, let's move it to the left. You have 1, 2, 3, 4, 5, 6, 7, 8. So this is now your decimal point. Therefore, you have here the original number in decimal notation. Get it? Or let's put it this way, class. A positive exponent is a whole number. A negative exponent is a decimal number. From the examples a while ago, we have here 20 sextillion. This is the whole number. The decimal centimeters as the size of an atom is a decimal notation, a decimal number. But both of them, do not be mistaken with my words I just usually use. The two of them are in decimal notation. Decimal notation. But this one is a decimal number. There's a difference, class, between a decimal notation and a decimal number. Decimal notation is the notation that we usually use as of the moment. This is based on the Dewey Decimal System, which is in base of 10. Computers simply uses the binary notation. Now, since computer language is understood only by ones and twos, diba? 0 and 1. No, not 1 and 2 pala. 0 and 1. 0 is off, 1 is on. Diba? Okay, so let's proceed. Okay, this one. Write this number in standard notation or decimal notation, class. 1.35 times 10 to the power of 5. So again, if the exponent is positive, move the decimal point to the right. If the exponent is negative, move the decimal point to the left. Or if the exponent is positive, the end value is whole number. So obviously, the decimal point goes to the right. If that is a negative value, the exponent goes to the decimal point goes to the left. If the exponent sign is negative. Since it is positive, therefore the decimal point from 1.35 goes to the right. So how will we do that? Simply move it to the right. Since 10,000, since 10 to the power 5 is equal to 10 For 100,000, you can also multiply 1.35 by 100,000, or you move the decimal point 5 places to the right. So therefore, the answer is 135,000. Okay? So to the right, positive, ha? To the left, negative. However, if it is from a decimal notation or standard notation, it's a different case already. If it is coming from a scientific notation or standard notation, we'll follow what is stated in the hint clue there I gave to you guys. If it is positive, you just have to move the decimal point to the right. If it is negative, you have to move the decimal point to the left. But what about if I will start with 25,000? If you're going to convert that to scientific notation, you have to move the decimal point from here, going there. So it will become 2.5 and multiply it by the base of 10, raised to the number of times the decimal point moves to the left. So this time around, since the given is a whole number, the exponent is positive 4. Changing this to a standard notation, since the exponent is positive, we need to move it 4 times to the right. Therefore, the answer goes back to 25,000. So, bali-bali rin sa class. So, from decimal to scientific, let's get the exponent to where the direction is in the opposite. From scientific to decimal, you get the movement to where the direction of the exponent, being positive to the right, being negative to the left. Kung balihon na to, o balihon sa nato ang sign. Clarifications? Yes, Alex.
Sir, about if we're going to convert to convert to 20 sextillion to scientific notation, sir, should it be 2.0 or just 2?
I will accept 2. I will accept 2.0, but still the same. The number of decimal, the number of significant digit is just 1, which is the 2. Okay. This 0.0 simply showcases the location of your decimal point. It could be
So
that
it's
the
okay,
answer is 2 times 10 to the power of 22. Okay na siya. It's just that the notation 2.0 tells us where the decimal point is located. But where do you think, sir, is the decimal point of a whole number? It is understood to be after the whole number itself. So understood na mo siya nga na diha. In other words, I will consider both with a 0.0 or walay 0.0. It's just the same. Alam. James?
Thank you, sir.
Sir, just to clarify, in your example, 25 times 10 to the power of 3 is wrong, sir, no?
25 times 10 to the power of 3 is correct but wrong. Okay. Let me write that one. So the answer here could be 25 times 10 to the power of 3. I say correct, but it's still wrong. Why? Because as a final answer, this is a wrong scientific notation, a wrongly written scientific notation. To write it correctly, we have to move the decimal point after the first significant digit. As in the rule, which is I said a while ago, move the decimal point after the first significant digit, and that is 2. After that will be the decimal point. There goes your answer, 2.5 times 10 to the power of 4 and not to the power of 3.
Yes, sir. Thank you, thank you.
Any other clarification? Please unmute yourselves if you have a question, class.
Sir, in the activity, sir,
Mhm.
there is operations already, sir.
That is why we still have to discuss that one.
Ah,
Don't be
sorry,
excited.
sir.
Don't be excited. Okay, the next one, if you don't have a question, then we'll proceed with addition and subtraction and multiplication and division. Okay. Go on.
What did Gil do there? He identified the variable that allow the entry of animals. That the condition was animals allowed and first.
Where is that? Yeah. So let's start with adding and subtracting scientific notation. Okay. So if you understand already, changing decimal notation to scientific notation or scientific notation to decimal notation, then perhaps it's high time for us to discuss operations on scientific notation. To start with, we have adding and subtracting numbers under scientific notation. So when you are going to add numbers in scientific notation class, you can perhaps change the number into standard notation, then add it. Let's say 1.23 times 10 to the power of 5 added by 1.24 times 10 to the power of 4. If maglibog mo to add it using the concept of scientific notation, then you can change it to standard notation and add the big numbers. And then probably the answer upon adding, you can convert it back again to scientific notation. Okay? However, the rule in adding and subtracting scientific notation class is simply, when adding and subtracting the numbers, simply look at the exponent of the base of 10. And the exponent of your base of 10 should be the same. Again, the exponent of your base of 10 must be the same when you are going to add or subtract. Let's have an example here. These are steps that you're going to follow, class. Step number 1, add and subtract the decimal. Step number 2, copy the exponent to the base of 10. Example number 1, 2.56 times 10 to the power of 3 added by 6.964 times 10 to the power of 3. Do we have the same exponent in your base of 10? The answer is yes. No, we have the same exponent, which is 10 to the power of 3. So therefore, step number 1, you add the decimals. 2.56 and 6.964 is equal to 9.524. Obviously, you need not to, sir, how to add, sir? Edson might ask, sir, how to add again, sir? So please don't ask me questions like that. Huh? So you are going to add the decimals, and the decimals are 2.56 and 6.964. So the result there would be 9.524. After that, bring down the exponent. Simply copy the exponent, which is 10 to the power of 3. So therefore, the answer is 9.524 times 10 to the power of 3. Let's proceed with example number 2. This is subtraction this time, class. So subtract 9.49 times 10 to the power of 5 minus 4.863 times 10 to the power of 5. So simply analyzing the given, they do have the same exponent, which is 10 to the power of 5. Or I mean, they do have the same base of 10 with an exponent of 5. So therefore, step number 1, subtract the decimals. And the decimals are 9.49 and 4.863. Sir, how to subtract there according to Edson? This is how to subtract, Edson. I hope you don't ask me questions like that, huh? Unlike grade 1, grade 2, probably I will answer that. But if you say, sir, how come the answer is 4.627? Huh? I don't know with you. You ask your calculator if you don't know how to manually compute it. Step number 2, bring down the exponent. The exponent is 10 to the power of 5. So therefore, the answer is 4.627 times 10 to the power of 5. Saya nagot siya, class. Saya nagot siya, actually. Okay, so let's have an exam already. ST3. On the spot. Okay, let's have a drill. Let's have a drill in addition and subtraction. Can I have... The first question goes to sige, bugbugon ako sa Edson. Edson, this is yours, Edson. The sum of 5.6 times 10 to the power of 3 and 2.4 times 10 to the power of 3. 5, 4, 3, 2, 2, 2.
Sir.
ABCD.
Um, wait, what? A.
A. Okay, the answer is A. Very good. Wow. James, Espanya, number 2. 8.0 times 10 to the power of 3 minus 2.0 times 10 to the power of 3.
6 times 10 to the power of 3, which is C.
Very good, ha? Update kayo. Nag-exam mo na, hindi na-cancer ba? Very good. So, how about we are going to, this time around, the previous examples class simply talks about similarity of the exponent of the base of 10. What about if they do have different exponents class? So this is what we're going to do class. When adding or subtracting numbers in scientific notation, the exponents must be the same. Otherwise, if they don't have the same exponent, make them similar. Okay, how will you make them similar? You know better how to do it. Either you move the decimal point of one given to make the same exponent then. Okay, it does not matter which number you are going to manipulate. Okay, in the previous example class, let's say for example here, if you have the exponent of 2 to be 2, 2 times 10 to the power of 2, so it's either you're going to change 8.0 times 10 to the power of 3, or you change 2.0 times 10 to the power of 2. It doesn't matter at all which number you are going to change, for as long as you can give me the correct answer. Of course, the correct answer is the correct way of writing the scientific notation. Let's try an example class here. Step number 1, we write the exponents to make it the same, and then step number 2, add and subtract. Step number 3, bring down the exponent of the base of 10. Okay, we have the example. Take a look at this example class. Add 4.12 times 10 to the power of 6 plus 3.94 times 10 to the power of 4. Layo kayo ang ilang gap class. Right? So therefore, if we're going to make it similar, either way, make 6 equals to 4 or make 4 equals to 6. Again, make 6 equals to 4 or make 4 equals to 6. How will we do that? In the solution class, instead of writing 4.12 times 10 to the power of 6, it was written as 412 times 10 to the power of 4. Just like the same as to the concern of James a while ago. No? However, how about we do that in the other way around? What happened? A while class.
There aren't so many, there aren't so many significant things that could happen in school on Saturdays and Sundays. That's why there might really be no need for a school bus.
Okay. So what about if we're going to solve this the other way around? Instead of writing the exponent of 10 here to become 4, why not make this equal to 6? Okay? So this will become 4. Rather, I'll do it here if you can see from here. Okay na ba? So we have 4.12 times 10 to the power of 6 plus. Since this is going to be made 6, so we have to add 2. By adding 2, we move the decimal point to the left. In other words, you have here 0.0394 times 10 to the power of 6. Okay? Again, how did we do that? To make this equal to 6, we added here the exponent, we added it with a 2. So therefore, we move the decimal point to the left. Okay? So we have here now. Yes, Miggy.
The 0 in front of 3 is a significant number or not?
Which 0? This one?
Yeah.
No, it's not significant. Okay, so to continue class, we have here 4.12, add it with 0.0394. So the answer would be 4.1594, which is basically the same as this one. No? In short, the answer then would be 4.1594 times 10 to the power of 6. And then the answer here, it's just using the first two digits, 4.15.
On Thursday,
Questions? We also have here another example class. Here, subtraction this time around. So making the first value 3 to become 2. So moving it to the right, so minus 1. So from 4.23, naimong 42.3. So we have 42.3 minus 9.56. You get 32.74 times 10 to the power of 2, or 3.274 times 10 to the power of 3. So whichever the case, you're going to change class, they will have the same answer.
I want to tell you this. Something like this can be done in a video recording. How do you expect to accomplish this
Take your time.
video recording? It can't be. And that means that you shall participate.
Okay, probably we'll have another example here. So we have here, rewrite the exponents class, either writing it as 10 to the power of 3 or 10 to the power of 6. It doesn't matter at all. So we are going to convert 3.4 times 10 to the power of 3 to 0.0034 times 10 to the power of 3 plus 3, or to the power of 6. And then we already have the same digits, the same exponents of your base of 10. So we can just simply add directly and then copy the decimal point, or copy the scientific notations base of 10. So we have the answer 2.46 times 2.4634 times 10 to the power of 6. Another example here. Let's convert 10 to the power of negative 1 to 10 to the power of 3 by adding it by 4. So when you add it by 4, you move the decimal point to the left. So we have 0.00265 times 10 to the power of 3. And there you have the numbers you're going to subtract. So the answer is 5.762 times 10 to the power of 3. Okay. Review the video I will send in the Mono Page class if I'm done uploading this in the YouTube. And also, there are tutorials in the internet that you can follow, especially in YouTube. Now, if you are confused of our discussion today, I wish I can share it in front of you guys and manually compute it in front, but the problem is we cannot do that. No? So if you're confused, kindly review the video, or if not, watch again some tutorials in the YouTube. Okay.